Hi, everyone, and welcome to Reducing Solar Foundation Risk. We are going to get started here right about now. And I would just like to introduce Jelica Mendoza. She's our program manager for solar foundation design. So she's really gotten a lot of hands-on experience both in the field and with the design principles behind it. So I'm going to leave it to her because she's the expert in this field to get right into the topic. Okay, over to you, Jelica.
Thank you, Janet, for the introduction. Very good afternoon to everyone who's joined in. Thank you very much for your time. My name is Jelica Mendoza. I am a geotechnical engineer and the program manager with PRI for the Solar Foundation Design Department. A little bit about myself. I joined PRI in 2019 after graduating from my undergrad and master's at Queen's University. Since then, I've been doing solar foundation design, managing over 100 solar projects, ranging in size from as small as 150 kilowatts to large utility scale projects. Doing geotech, managing the pile load testing programs, and as well as construction QA/QC. So today I'll be talking about a topic that may not be as obvious from the ground surface, but something that can bring a lot of risk to your project if not thoroughly investigated and prepared for. And so today I'll be talking about how to reduce that solar foundation risk for your project. And before I get started, a little bit about PRI. If you're new to us, we are a small group of geotechnical consulting engineers with over 100 years of combined experience. We've completed over 300 projects since we started in 2019. From preliminary studies to detailed design and construction support. And in fact, we don't just work on solar projects. We do a whole lot of other geotechnical range of services. We have a CCIL certified in-house laboratory in our main headquarters in Lindsay, Ontario. And we do materials testing for soil, aggregate, and concrete for all their geotechnical needs. And in fact, I'm happy to announce that we are close to getting certified for our new in-house laboratory in Calgary, Alberta. So stay tuned on updates on that. So quick agenda for the day. I'll be starting with a bit of problem definition. Talk about what exactly the risks are when it comes to foundation design. And I cannot talk about geotechnical risks without briefly touching on frost uplift and how that affects your foundations. A little bit about how we predict frost heave, how to manage those foundation risks, and finally conclude with a case study for a site in Summerside, PEI. So to start, and I'm sure you're all here today because we know how economical solar generation systems are becoming more and more. And so one thing that I would like to note is the difference between a solar project compared to the other traditional conventional infrastructure is solar projects involve a large number of lightly loaded pile elements compared to your conventional structures. For example, one site in Alberta, we had over like 250 piles for just that one project. And so you can imagine that every foot of savings you can make with your foundation design, that can translate to a monumental effect when you look at it in full scope for 250,000 piles. So there's definitely a lot of desire in optimizing that design to create some savings in that front. And we can't do that without considering the risk of failure, risk of generation loss, and the overall costs of those foundation elements. And in order to do that, we need to have a better understanding of the overall frost uplift design when it comes to cold climate regions. So if you're new to frost, I am not going to go into too much detail here, but real briefly, frost uplift is caused by the expansion of the water inside the pores of the soil grains as the temperatures freeze over time. And using the analogy of sticking your tongue on a frozen pole, you know not to do that because it's going to create a bond between that steel and that frozen material. And in the case of frozen soil, as your pore water freezes and expands, that can translate to heaving of the pile as the soil moves. And you can see here in the picture in the middle what that can do to your foundation elements. So we have an example of a concrete foundation for a racking system that has heaved by, and you can see at least a foot above the ground there due to frost jacking. And if you have these multiple foundation elements experiencing frost uplift in varying measures, then you can have like a differential displacement between those piles, and that can cause damage to your PV racking system and your modules, like what's shown on the right-hand picture over there. And so I'm definitely not going to go into detail on how we calculate frost uplift loads, but I did want to mention where it stems from. So we use the Foundation Engineering Manual to come up with the frost uplift load calculations. That is what we use to design the piles. And so that involves calculating your frost penetration depth, considering your pile perimeter, the add freeze bond stresses, and applying factors of safety to that. Now, the Foundation Engineering Manual was designed for a more general range of applications. So one thing that solar foundation experts do is we consider modifying that using the recommendations by Becker in his conference paper published in 2017, modifying that for lightly loaded structures, such as what we have for solar foundation elements. And so a part of that is also considering the frost penetration depth for your site, using your site-specific local climatic data to further optimize what that frost load is for your site. And so we analyze that for mean and maximum frost depth. And this is all to fully optimize the design for your site. So I'm going to take you through an example site, a 32 megawatt in Alberta, where we used a driven pile design, and the process that we took in from the geotechnical investigation to the testing program in trying to understand the frost uplift design and how to calculate the foundation length for the project. So we started by reviewing the geotechnical report, which was completed by others. So we reviewed it, and we know that the site was underlain by sand and clay. There were boreholes that were advanced on site, and in the chart on the right-hand side, you can see an example of one of the main parameters that we look at when reviewing borehole data, which is the SPTN values, and that's essentially the number of blows that'll take to penetrate the soil by a foot. So using that, we gauge the properties of the soil that will help us as input into the frost load calculations for these piles. So we had a W6 by 9, a W8 by 10. And in the table at the bottom there, we calculated what the frost uplift load would be for both of those cross sections. And before I move forward, just a note on geotechnical investigations in general. So here we had boreholes, but there will be other sites as well where test pits could also be beneficial. And for example, if you're anticipating obstructions, cobbles, boulders, or bedrock material in your site, test pits could also be the way to go, because that will allow for a direct observation into the size and frequency of that refuse material that you may be encountering, compared to what you'll be able to see in a 6-inch borehole. So after we reviewed the geotechnical report, we also did some pre-production load tests. So we sent our crew to the site to perform axial and lateral load testing on some test-driven piles. And you can see in the photo over here, we used our reaction frame version 3.0 after some modifications to pull the pile for axial testing. And then using that, we also made some more efforts in trying to fully understand how to calculate the frost uplift loading. So we've done the geotech, we've done the pile load testing, but one thing that we really needed to understand more is how to predict that frost heave pressure. Because talking about the foundation engineering manual earlier, the real guideline that we only have to this day is just the numbers provided by the foundation engineering manual for providing a number for that frost heave. So we took some more steps. We started getting involved with the University of Western Ontario last year to try and do some research and fully understand what that value for frost heave entails and how to get that. So what we did here is we used some real climatic data for that same site that I showed you a couple slides earlier. And you can see here in the chart, the temperature data, it drops down to the minimum temperature in the first 100 days when the soil starts to thaw, and then it goes up again after 200 days. So this is a typical freeze thaw cycle for the site. And then we had our friends over at Western use an analytical method by Ladani and Ferrero for establishing what that rate of heaving is and quantifying that stress using this complicated equation that I'm not going to go into detail as well. But what I wanted to show you here was the results so far in our studies is how we try to model that stress and what that means for your foundation design. So here I have the same graph. So on the x-axis, I have the first 200 days when the temperature drops down to the minimum on both charts. So the difference between these two is on the left, we have the average shear stress of the soil bonding to the pile in kPa. And then on the right-hand side, it's essentially the same information, but we have that stress converted to a force in kilonewtons. And what Ladani and Ferrero in their paper, what they theorized was a slip phenomenon. And before I go into the graphs over here, so what they found was that they have a theory where as the soil freezes, it causes a movement to the pile. And when you reach a certain number of deflections, so when you reach 2 centimeters of deflection, there's a slip or a breakage in the bond between your frozen soil and the pile, such that the soil is unable to fully transfer that pressure from the soil to the pile. So your pile doesn't fully experience that full stress that we conventionally estimate from previous methods. So to fully illustrate that here, so we have two curves, one blue and one orange. So the blue shows you what that stress means as the soil freezes. So you got at 20 days, when the temperature drops, you start to have an increase in that stress from the soil, and it reaches a peak at about close to 200 kPa when you get to 60 to 80 days, which corresponds to your minimum temperatures. And then when the soil thaws, your stress also starts to dip down from then on. But when you look at the orange curve, if you consider this slip phenomenon, it starts to peak at 150 after 20 days, but it doesn't continue on. It starts to drop from that moment forward and continues to drop down until 160 days. So it doesn't fully reach that full 200 kPa stress. On the right-hand side, so we just have the kilonewtons force for that material. So the blue curve looks essentially the same, going to about 200 kilonewtons at the peak, but for the orange curve, you only get to about half of what we initially expect from the no slip case. So what does this all mean to our foundation design? So when we try to calculate the frost uplift load for a pile, so here, for example, we have a 6x9 getting 259 kilonewton, an 8x10 getting 282 kilonewtons. So these are the design loads for the pile that we directly use to calculate how long your pile is going to be for your site. And as you can see, the 159 and 182 closely matches. It's pretty close to the blue curve over here. But if you consider like what actually happens to the actual frozen soil material, there's a potential that we're not really reaching that full 200 kilonewton force, that maybe only half of that force is being applied. So what I'm trying to bring across here is, yes, like this is something that we're still investigating, something that's still being studied and hasn't been proved yet. But as engineers, the challenge here is knowing the difference between that blue curve that results from factoring your design loads and what that real value is, and trying to find that happy medium and the optimum value, so that you're not over engineering your piles. That can result in, like this difference can result in like 10, 15 meter piles for your solar foundations, when maybe all you really need is 5 or 6. So the challenge here is understanding what that range is and doing enough studies and testing to figure out what that right value is. So in order to do that, it definitely takes a lot of experience and a lot of work. And here in this slide, I'll take you through the different steps that you can take as an owner or a developer to manage those foundation risks. So on the left-hand side, I'll talk about like the different steps that are already of common knowledge. And on the right-hand side, I'll talk about a little more of the extra bits that you can do, the extra steps that you can take to really manage those risks. So let's start with a desktop study. So before you start your project, you want to know how feasible the site could be, and that can involve looking at soil, rock, groundwater data, and that's primarily based on published mapping or historical groundwater well records, and taking that information and looking at the feasibility of the site. One extra step that you can take is to send an expert to site to do a preliminary site visit. It can just be like over a few hours to half a day, And what we do there is we look at the access conditions of the site at the time of the project versus what the mapping can give you. So we look at site features, we look at maybe some infrastructure that were developed over time that wasn't necessarily recorded in the historical records. So things like that can go a long way. Next, you'd want to do a geotechnical investigation. That can be test bits or boreholes. But one thing to note is doing a geotech with a solar focus. And what I mean by that is really understanding what in your scope is important for developing your racking foundations. And for example, when you do boreholes, if I were to design a program for a skyscraper, for example, I'd probably put in 100-foot boreholes down there just to really understand the soil properties to that depth for the potential depth of our footings or foundations. Whereas for a solar farm, I probably put in 20-foot or maximum 30-foot boreholes. Definitely not 100-foot, and you wouldn't need that to develop solar foundations. So that's just one example of really honing in on what you need for a solar geotechnical program. Next, you'd want to do a pre-production pile load testing. So when we do pile load testing, there's a lot of work that actually comes with that. So before you go to site and put some test piles in, it's important to do some preliminary foundation design first, which involves considering your frost loads, your racking loads, before you actually put some piles in the ground. That way you can target a certain embedment depth of certain locations in your site, and you're putting more thought into what could come out of your pile load testing program. And maybe you can go straight to doing a detailed foundation design with that. But an extra step you can actually take before you go into construction is to do what we call like a phase 2 load testing program. And there are many reasons why you may have the desire to come back to site. Maybe like on the first stage of your project, you realize that there's actually more, there's a more heterogeneity in your soil or varying subsurface conditions. So maybe you want to put more piles in to get a better resolution of your site. Or maybe the initial piles you tested weren't exactly the right type. Maybe you started with helicals and now you want to try driven piles, or maybe you want to do a different cross section. You want to do driven W's and driven C channels and driven round posts. So there are many reasons why it might want to come back, and especially for large sites where there could be just so much variability. So one site I've recently worked on, we had like 5 different zones, because on one end of the site we had some nice fine clay, and then on the other end of the site we suddenly have cobbles and boulders, and then the other end of the site we had more sand and gravel. And these different soil conditions may mean that you need multiple different foundations for your site. And then after that, during construction, we would also highly recommend doing a rigorous quality assurance, quality control program, because it's not just about designing for the right foundations, it's also about installing to the right specifications to make sure it meets that design. So something we highly recommend is doing the QA/QC and also verifying that the piles were built to the right conditions by doing some production load testing of the site. So in the last part of my presentation, I do want to touch base on a case study for a site that we did in Summerside, PI. And for this site, when we were initially called in to do the work, they've completed the geotech already. So there was a report that was produced, and the initial intention was to put in helical piles in the ground. So when we reviewed all the information from the geotech, we realized that there is actually shallow bedrock in the site. And we knew right off the bat that helicals may not be the right foundation types for this because of the presence of cobbles and boulders or other obstructions that can cause premature refusal to the helicals. So before we went forward, so we considered that information. We also did some frost analysis, such as the previous slides that I talked about. We did some corrosion design analysis, and then we carefully crafted a pre-production pile load testing program to put in some driven piles, which I'll talk about on the next slide. And in parallel to that, we also had the racking team do their design considerations for structural loading, considering that there were high winds and snow loads in the area. They looked at topology, module bonding, and all those details that I personally wouldn't be able to provide details with, but just so you know that the polar racking team was also involved in that racking design aspect. Okay, so we sent the PRI crew to site to do some load testing. We put in there's two types of driven piles. We did driven W sections and driven round pipes. And so the main parameter that we record or measure when we do driven pile load tests is called the skin friction. And so when we did the round posts versus the W sections, we measured those skin friction values that we get from pull testing. And what we found was that the round posts produced a higher skin friction, in fact, around 2.4 times greater than what we got from those I-beams. And we were also having difficulties driving the W sections into that weathered bedrock, whereas the round posts had a better chance of penetrating that soft layer of weathered bedrock. And then later on, we also did some rigorous QA/QC at the construction stage and also developed some remediation design. So a little bit more on that load testing. And we would like to really stress like the difference between that round HSS versus the W section, because we found that the round posts were just so much more successful in penetrating that material. And this wasn't the first site where we observed that. We actually had another site in Alberta and another site in the Caribbean, where we found that the driven pipes were just so much more successful in penetrating that layer of bedrock. And when it does, it really gives us that extra bit of resistance within that bedrock. And what sits in there, it's locked in, and you're just unable to pull that pile out because of that extra resistance. So that's like the optimum or the ideal design right there, is if you lock into that bedrock material. So the reason why the W sections weren't as successful is if you look at the cross-section diagrams here at the top right corner, when you have an I-beam, like, and you drive that pile into the soil, yes, there's like a soil plug that forms, but as you drive the pile in deeper, that soil plug shears from the rest of the soil around it. So it doesn't really effectively do anything. Whereas with your round pipes, because of that constricted space around that pipe section, you get a soil plug that effectively acts as a plug and stops and is able to shed those cobbles and boulders as you penetrate that soil with a pipe versus what you get with an H pile. So that's one of the reasons why the pipes were more successful. And at the bottom here, you also have, we tested about like 22 piles, and for each pile, we recorded the skin friction values for 6x9, which is gray. And then we have the blue curve here for a pipe, and you can see the difference in the range of skin friction values between those two. And as I mentioned previously, on average, that pipe was 2.4 times greater in skin friction compared to the W6x9. So that being said, we went with a driven round post as our main design. And little did we know that we were about to have the true test of nature. Late September last year, I'm sure you've heard Hurricane Fiona swept in, and that included our site in Summerside. There were millions of reported damages across Atlantic Canada, an estimated of 2 billion to 4 billion in economic losses across the region. And we're happy to announce that from our side, the Summerside site was able to withstand that test of time. On the left-hand side, you can see the before, and then on the right-hand side, you can see the after. There was very minimal damages to the foundation elements and the racking system. In fact, it was only like, there were only a few tables that have not been installed yet on site that were just in storage. They're like only those sustained the damages, nothing that was standing had been touched. So with that, I would really like to stress how important sound engineering is, and without sacrificing functionality, but also thinking about the economic aspects of the site, coming up with a truly optimized foundation design after taking the necessary steps from desktop study to geotech to a sound pile load testing program, and coming up with this well-designed structure for the site. And of course, it wasn't just the foundation engineering team. I would also like to thank the owners who made the right call in doing all of these development stages, the racking team, the site team, who overall put in a good collaboration effort to come up with a good site. And so with that, I will end my presentation and welcome any questions. Feel free to drop in your questions in the chat box, and I'll start addressing them shortly here. Thank you very much for listening.
Thanks everyone for attending. And if while we're waiting for any sort of questions to come in on the chat, if you just click on the bottom of your screen, you'll find the chat box, and you can just simply ask Jelica a question directly. Jelica, is there anything, while we're waiting for some questions to come in, any aspect of solar foundation design that you didn't get a chance to cover here that you really like to talk about? I know it's you have a limited amount of time that you can talk about, so maybe there's some aspect here that you can talk about.
I might go back like a couple slides here to give you guys a few minutes. Okay. Yeah, so I don't want to go into too much detail on frost uplift load calculations, but I think one thing that's important to really understand is, like, solar industry is pretty new, and well, we only have a foundation engineering manual that was published in 2006 using data from the 50s, right? So one thing when you're doing frost uplift design is noting how, it's now 2023, and we all know what the trends in climate, right? Global warming. So if you're using data from the 1950s, you just need to have a mind what that can lead to in your frost uplift calculations. So here at PRI, our philosophy is to use local climatic data. So what we do is we take the most recent 20, 30-year data set for the specific site, and then we use that and analyze that to come up with an average and maximum frost penetration depth. That way, we're not overestimating what those temperatures are, and that doesn't lead to an overestimated frost penetration depth to your site. And that can be a difference like of a 2 meter to a 2.5 meter frost depth, which can make like a meter difference in your pile length. So having that in mind and having that understanding is one of the key things that we do here at PRI, is truly honing in on what the real parameters are for your site and using that as a basis for the design.
So we have had 2 questions come in. One's
Sure.
from Carl Feniak, and he says, or he asks, what are your thoughts on A-frame foundation structures for use in Alberta? And then we have a second one too, and that's from David Kaplan. So why don't we start with the one from Carl Feniak, please?
Sure. So what are your thoughts on frame foundation structures for use in Alberta? Frame foundations. So I'm not familiar with that. Can you?
So A-frame.
Oh, A-frame. Okay, gotcha. A-frame foundation structures. So like for testing purposes, you mean like the picture here on the right? And my apologies.
I think he means the A-frame foundation, like the actual racking structure.
Oh, for the racking structure. There might be some for use with SAT tables. Oh, okay. Gotcha. So I haven't personally seen those A-frame foundation structures for SAT tables. So maybe someone from my team can follow up on that. I'll have to get back to you. Sorry, Carl.
Okay, and then the next question from David is one that I've had myself as someone who's not an engineer. He asked, what is the difference between slip and like what without slip? So what does that mean?
Yeah, no problem. It is a bit complex. So I'll try to explain it again to the best of my ability here. So like going back to like the frost heave phenomenon, like it's basically the expansion of soil as it freezes, and as the soil freezes, it also adheres to the steel post that's in the ground, and so when that soil moves, it brings the pile up with it during that movement. So there's 2 cases or 2 ways that can happen that conventionally, like we can think that of there's no slip phenomenon. So with the no slip, it just, when the soil moves the whole time, it will just transfer that stress onto the pile, and then your pile heaves fully with it during that entire process. So with a slip, there's this theory that after the soil moves and reaches about 2 centimeters of movement, that is enough movement to break the bond between the frozen material and the steel, such that it doesn't fully transfer the stress from the soil to that pile. So instead of continuing to move past the 2 centimeters and continuing to experience that full stress, the stress actually starts to go down from that moment forward, and the pile doesn't fully experience that full upheaval force. So in quantifiable terms, instead of 200 kilonewtons, we only achieve about half of that force, which is about 100 kilonewtons. And I hope that makes I hope that helps.
Okay, and so David just has a follow-up from that
Sure.
question, and then we'll move on to another one. So he's saying you would use it is a different pile type for slip versus no slip.
So not necessarily. It's just so with it's more of a driver for your design load. So you can use the same pile, but for a no slip version, you might need like a pile that's 1 meter longer than the no slip pile. So it directly drives your design loads, and based on that design load, the engineer will calculate what that pile length is required for to fully resist that design load. So maybe for a no slip, that might mean you need a 6 meter pile, but if it would have been a non-slip case and a reduced design load, maybe you only need a 5 meter pile, just for example. So it's the same pile, not necessarily different pile, just different embedment lengths.
Okay.
Your load.
Perfect. And then Peter asks, are there instances that inform the use of board cast in situ piles as a solar foundation option?
Yes. So the site could have very challenging soil conditions. So there may be cases where you do need to start thinking about concrete, because the bond between the concrete and soil, it is superior to other materials. However, it can also cost a lot of money. So there are different site conditions. I won't go into detail, but yes, there are some instances where that would be the case.
Okay, and then
a bare steel pile is not enough to resist your loads.
Okay, and then we have an anonymous participant that asks, which piles are best for axial and lateral load testing in conditions like Alberta?
In conditions like Alberta, so most sites, like it's always a good idea to really do the geotech and find out what the different conditions are, because it can vary. Maybe the conditions are more conducive to drivens, maybe helicals. It can vary, like even from one site to another, that's like kilometers apart. There could be some small differences. So the most common ones that we've worked on in general in Alberta are driven piles and helicals. Because of so driven piles, in most cases they could work if like in glacial till material, or in soft sedimentary bedrock. As I've mentioned earlier, the driven pipes are a good one there. If there's not enough skin friction from the soil, like if it's not hard or dense enough, then you might start thinking about helical piles as well to get that extra capacity, bearing capacity from the anchor.
Okay, that just about does it for any questions that we have. So I just wanted to thank everyone who attended. And if you do have any questions, Jelica, if you want to put the slide to the last one, please feel free to reach out to us directly, and we can answer any questions that you may have about any part of the presentation. All right, so thank you very much, everyone. And we're going to end it there. And thanks, Jelica.
Yeah, no problem. Please reach out to us if you have more questions.